Assalamu alaikum. In this lecture, we are going to talk about the directional ground fault protection. In the previous lectures, we have already covered the 30-degree and 90-degree connections. And we also talk about that how can we decide about the ICC, which is the current coil current, and VPC, which is a potential coil voltage. And we also know that the formula for the torque in the directional relays is tau is equal to tau max, where tau is the torque, cosine theta minus tau. So you can say this is torque and this is the maximum torque angle. This theta is the angle between the ICC and VPC quantities. So this tau max is equal to KICC VPC. When cosine value is equal to 1, we have the maximum torque. So we have already covered all these different topics. Now in today's lecture, we are going to talk about the directional ground fault protection scheme. In case of line to ground faults, we know that the fault current is equal to 3I naught. So this is a zero sequence current. And in case of a ground faults, we have IF equal to 3I naught. And all the single line to ground faults are known as ground faults, and all the line to ground faults, they are known as phase faults. So we have AB, ABG faults. Both of these faults are phase faults. So in this part of the lecture, we are only talking about the line to ground faults, which are known as specifically ground fault. So from the sequence network analysis, we know that the fault current in case of a single line to ground fault is 3I naught. So we are going to draw the phasor diagram that what should be the VPC if we have a fault current 3I naught flowing in the circuit in case of single line to ground fault. So firstly, we will draw the pre-fault voltages. Suppose this is EA, this is EB, and this is EC. So the voltages that are denoted by E are the pre-fault voltages. And once the fault occurs, we have a voltage VA in the faulted phase, and the current IF equal to 3I naught flowing through that particular phase. Right? Now we have to decide about the VPC, that what should be the potential coil voltage in case of ground faults. By using the same methodology that we have used in the previous lectures in case of 30, 60 and 90 degree connections, we know that in this case the VPC will be equal to VA plus VB plus VC. So this is the voltage of phase A in which the fault has occurred. And now if I have to show the voltages of the other two phases, that will be VB and VC. Because the fault in this case is occurred in the phase A, so the voltages of phase B and phase C will remain same. So now we know that VPC will be equal to VA plus VB plus VC. So now we have to check the operation of the directional relay. So for that we have to first draw the VPC phasor, which is VA plus VB VC. So this will be the VPC phasor. And if this is the VPC phasor, the MTA line will be somewhere around 20 degree from the VPC phasor. So this is your MTA line, and the zero torque line will be at 90 degree from the MTA line. So this is the zero torque line, and this region will be the restraint region, and this is the trip region. So the fault current is in the trip region. So if we will use the VPC, which is actually the summation of VA, VB and VC, then the potential coil voltage value will be providing you satisfactory results in order to detect the directionality in case of directional ground faults. So what are the inputs of the directional relay in case of ground faults? 3I0, which is actually the fault current, and VA plus VB plus VC, right? So this is the VPC value, and we also know that 3I0 is equal to IA plus IP plus IC from the sequence network analysis of the single line to ground fault case. So this was the explanation of the directional ground fault protection. Now we will move on towards the three-phase feeder protection, and in the three-phase feeder protection we are using directional as well as overcurrent relay. So we have to provide protection to the three-phase feeder. So we have used two-phase relays. This is VAB, so we have used two phase relays. This is phase relay 1 and this is phase relay 2, and one ground relay. So this is your ground relay. From the previous discussion we know that the input to the phase relay is a line quantity, a line voltage quantity, which is VPC. In this case we have VAB, and the current IC is flowing through the current coil. Similarly, for phase A we are using the VBC value as a polarizing quantity, and the current IA is flowing through the current coil. So this is your directional element, and this is the simple overcurrent relay. This is for phase C and this is for phase A. For the ground relays we have to use summation of voltages VA plus VB plus VC here as a polarizing quantity VPC, and the current should be 3I0, and this current is coming from phase B, right? So if we have a fault line to ground fault in phase B or phase C, in both the cases we will have the current equal to 3I0. So we don't have to use the ground fault relay separately for the three phases, because we are using the currents from all the three phases as an input to the directional element of the ground relay. So the current in case of ground fault will be 3I0 and will surely be passing through the ground relay. So we have two phase relays P1 and P2 and one ground relay, that is G, and here the contacts are shown. So if the overcurrent relay is being operated, firstly the directional relay should also operate, or the directional element of the relay should also operate, otherwise there will be no signal to the trip contacts. Similar is the case for the ground relay, because this is the ground relay. If the directional element is not operating, then the overcurrent relay, whether it is operated or not, will not have any effect on the trip contact signal, right? So we know that we have to get the values of current and voltages from the three-phase feeder. So here are the potential transformers that we have used for the measurement of voltage VBC, which is the input to the phase A relay, and VAB, which is the input to the phase C relay. And for the VPC value for the ground relay, we have to use the summation of A, B and C voltages. So we have taken voltages from all the three phases, and in the secondary of the transformer we are just adding all the voltages because we have attached all the coils in series. So this VPC is actually the summation of VA plus VB plus VC, and we have used these voltages here, here and in the ground relay here. So in this way we can provide protection to a three-phase feeder by using only 3 relays. 2 are phase relays and the 1 is ground relay.